The next type of special product that we're going to be talking about is called the difference of two squares. So the reason why it's called difference of two squares isn't going to become apparent until we do a couple problems. So let's just try this for a minute and then we'll talk about why it's called that. So if I take 3x plus 4 times 3x minus 4, if I just distribute like normal, 3x times 3x is 9x squared, 3x times negative 4 is negative 12x. Then I come back and grab the 4, and 4 times 3x is plus 12x, and 4 times negative 4 is negative 16. What happens here is the like terms in the middle, negative 12x plus 12x, add to 0. So I'm just left with 9x squared minus 16. Okay, so that was an interesting case where the middle terms canceled out. Let's try another and see if the same thing happens. X times x is x squared. X times 5 in green is 5x. Now I'm going to come back and grab the negative 5 and distribute that. Negative 5 times x is negative 5x. Negative 5 times 5 is negative 25. And again, the middle terms, 5x and minus 5x, add to 0, and I'm just left with x squared minus 25. The two middle terms canceled out again. One more problem, and then we'll try to figure out if there's some patterns here. A times a is a squared. A times minus b is minus ab. B times a is plus, and I'm going to put the a in front of the b just to keep it in order. And then we have b times negative b, which is negative b squared. Once again, minus ab plus ab, negative 1 plus 1 adds to 0, so that those like terms cancel out, and you're just left with a squared minus b squared. Okay, so what do you notice about that's similar about all three of these problems? Well, the 3x and the 3x were the same, and the 4 and the 4 were the same. The only difference is the sign in the middle was different. So 3x plus 4, 3x minus 4. X minus 5, x plus 5. Notice that the terms in the front and the terms in the back are the same. The only difference is the sign. In a plus b and a minus b, again, the terms were the same, but the sign in the middle was different. And when that happens, the two middle terms always canceled out. And all you're left with is the square of the first term minus the square of the last term. That's where this word difference of two squares. Difference means subtract and two perfect squares. So if I had a squared minus b squared, that's a difference, the minus of two squares. Notice it always comes out to be two perfect squares being subtracted. This happens every time that you have two polynomials being multiplied that are conjugates. A conjugate would be if the terms are the same but the signs are different. And that word conjugate, this is how you spell that, conjugates. So if you ever have conjugates being multiplied, you can just use a rule to get to the answer a little bit more quickly. Now, if you want to distribute it out the long way, you can always do that. In fact, everything from today's lesson special products can be done just by double distributing. But we're just trying to show you some special cases here. So the rule for difference of two squares says when you're multiplying two binomials that differ only in the signs between their terms, you could just subtract the square of the last term from the square of the first term, or a squared minus b squared. So instead of distributing x plus 3 times x minus 3, I could distribute it, but I'm trying to use the rule. To use the rule, I'm just going to take the x and square that, so x squared, minus, and take the common 3 in the back, and that's 3 squared. So x squared minus 3 squared is just x squared minus 9. Now, if you're like, I don't know if that's right, you could do it the long way. I'm not going to do it the long way every single time because we're practicing not. I'm just trying to prove to you that this rule does work. So x times x is x squared minus 3x plus 3x minus 9. The two middle ones are always going to cancel out, so then you'll get just the x squared minus 9. So I did prove it that it's going to work, but I'm not going to do it every time. So on the next one, a minus 2 times a plus 2. Are they conjugates? Yes, they are. So we're just going to get a squared minus, because the formula says so, and then you're going to take 2 squared, which is 4. And that's it. On the next problem, are they conjugates? 9x plus 1, 9x minus 1? Yes, they are. So I'm going to take 9x and square that. 9x times 9x is 81x squared. Then we have a minus because the formula says so. And then we have 1 times 1, which is just 1. You're welcome to distribute it the long way if you really want to. It will come out the same. The next one, we have two conjugates, 2x plus 5, 2x minus 5. So I'm going to take the 2x and square that. 2x times 2x is 4x squared. Notice that I'm squaring both the 2 and the x because that's a monomial, so that I can distribute the 2 across it. Remember, if it was a binomial, if there was a plus inside, you're not allowed to do that. But because there's no plus inside, it's a monomial, and you are allowed to distribute it. Minus because there's a minus in the formula. And then 5 squared. And 5 squared is 25. Now we have 3a times 3a, which gets you 9a squared. And then we have a minus because there's a minus in the formula. And then we have 7b times 7b, which is 49b squared. Now, if you want to jump straight to the answers on these and not show any work, you are fully welcome to do that. And then on our last one, we have 4x being squared, which if you can just get 16x squared initially without having to write that out, you're welcome to. Minus because there's a minus in the formula, and then 3 squared, which is just 9. Notice that each one of these numbers is a perfect square. 4, 25, 9, 49, 16. These are all perfect squares, which follows the rule difference of two squares. And this concludes our lesson on special products.